You do the sweeping here, and then after that you actually cool it back again, and then it goes to the adsorption. So you might need an intermediate cooling step or before it goes to adsorption. It really depends. Some of the Jordans, if you do not cool it, it will break through immediately. For some of them, actually, you can skip the cooling step completely. But generally, if you're doing a temperature swing adsorption, the idea is that instead of pressure, you raise the temperature during desorption and then cool it back again before the adsorption. So that's the overall process. Now the question is, how do you heat it up? So remember here I just said hot water. You can use steam, for example, for heating up the bed. But remember, if you're using the steam for heating up the bed, steam by itself does not give you much energy if you do not condense it. The main energy content in the steam is in the latent heat of the condensation. But if you're not condensing it and you're just saying, oh, I want to use the sensible heat, you need massive amount of steam that goes through the system. So it's usually not worth it. So putting it within a hot water and actually can really help you from that perspective. But this is all about that what you need to do for temperature swing. Does yes.
Inside the bed, like bed completely moist.
It's not desired actually. So you cannot condense it within the bed. That's the problem. So if you do not condense the steam within the bed, that means the amount of heat that you can get from steam is only the sensible heat, which is very low. That is why it's not a good idea to use steam for heating. If you use steam, it's only for reducing the partial pressure. So you can use some direct steam injection during temperature swing. So I'll be so you are right. If you actually the steam condenses, it will be actually lump. And interestingly, I know one technology developer who was actually trying to do something like that for a moving bed. Actually, it's the solid cease to flow because it formed lumped and the bed will not flow through the system. And the problem is that from the boundary condition, it was not showing that the water will condense. It's because of some capillary effect somewhere inside it was actually condensing, which we simulated and we found out somewhere in the middle, it is actually going to the condensation conditions there. But what I would like to mention here is that steam should not condense in the bed. If direct steam injection is considered for heating, only sensible heat content in steam should be used. So it may require very large quantity of steam. Direct steam injection, it does not mean that you should not use it. Direct direct steam injection can help to lower the partial pressure of CO2, so help in regeneration. Right? Mm-hmm.
Another question is now, what CO2 for dissolved?
Uh-huh.
What happens in case of evaporation? Air becomes saturated with moisture. Like that, it happens because the partial pressure of CO2, already 100% CO2 you are passing and you want to dissolve CO2, so
Right.
you are at the end of the isotherm.
Yes, so you might require a higher temperature if you are using CO2 there. The other thing we have to also remember, if you are using a gas like CO2, gas CP is very low, as we all know. Like specific heat of gases is very, very low. So if you want to provide this 65 kilojoule per mole or 100 kilojoule per mole, you have to send actually massive amount of gas through the system. It does not matter whether you use CO2 or nitrogen or anything. This is because of the scale that at which we want to go to, because of the amount of heat needed is very high, and generally gas, providing it with a gas sensible heat is not a good option unless there is a very hot gas, like you say I have a 500 degree centigrade temperature gas that I can pass through, but that may not be acceptable for the adsorbent. That high temperature may not be acceptable, so we have to keep those things in mind. Anything else here? Okay, the other thing is that this this is also from Ryan's paper, because we really wanted to look into this. So we consider two processes. One is like we call a basic TSA process. Basically, idea is that there is no cooling needed during adsorption, and during desorption, we have a heat exchanger here, and we put the steam inside the heat exchanger. So it does condense. So instead of hot water, I can put steam inside this one and it will condense and come out. So this is one approach. But you see that there is also a steam being injected over here. So this is the direct steam that I was talking about that helps you to reduce the partial pressure of CO2. This steam is not for heating. This is the steam used for heating. So the problem here is that you are not able to cool it here. So now if you actually use it for cooling purposes, so you can use a cooling water. If you put a cooling water here, for the desorption step, you cannot put a steam in the same coil, because just to ensure we understand the question. Say I put a cooling water, so I have a coil here. Instead of keeping it empty, I can put a cooling water through here for adsorption. And then what I do is for the desorption, you see that we are suggesting you put a hot water. Instead of hot water, once the adsorption step is done, I can inject the steam inside here instead of hot water. What would be the issue? Right, and so what would be the problem there? Because if steam condenses, I'm getting the heat anyway, so I'm happy with it. It's an industrial problem, it's practical. Sorry? Let's say we keep the similar temperature that I wanted. There is something called a hammering, water hammering. So it will lead to water hammering, because the steam will try to push the water and it cannot actually, because steam travels at a much higher velocity. So that is why we always have the condensate removal and all of those. So it's a practicality problem. In real life, you cannot use it. Mathematically, you can, but it will cause the water hammering if you introduce steam directly into it. So that's why we proposed when you use cooling water, use hot water. So and then the hot water is heated elsewhere by using steam in a heater, and then it just keeps circulating. So that's how it is. Now, this gives you some of these things here. We consider bed length like 10-meter, bed diameter 10-meter, blah, blah, and all of that. The reason I wanted to show you here is there are some interesting results I wanted to show. I think actually maybe I will, okay, maybe I'll discuss that actually after this slide, but this one connects to some other slide later on, but this is overall thing. I'll come back here later on. Okay, the other approach is to doing the vacuum swing. This vacuum is actually pulled for regeneration. So basically you pressurize it, adsorb it, depressurize it, evacuate it, and that time it basically, if you have strongly adsorbed CO2, like more because of the chemical reaction, then you might require vacuum here. So that is where you do the vacuum. And you can also do an inert purge like nitrogen and steam, etc. And you can actually use those things for purging the overall system. So that is basically the whole idea of the vacuum swing adsorption. All of these actually can be used in combination with each other. So I can do simultaneously pressure and temperature swing. I can do, and we'll be talking about that, some of these other approaches where you pressurize it and then you actually pulling it out, you do the vacuum swing. So all of those approaches, these can be combined. These are not exclusive. You can do a combination of all of those. And that is where your design space become larger and larger and larger, right? Any question here? Okay. If not, I will now go into how this will actually look into. So think about like a power plant. So how it will operate here is, again, this is from Ryan's paper. So this is the gas, this is coming to a compressor or a blower, and you see how these are actually put into the system. So if you have a parallel bed, these beds will be in series and in line. So these are empty valves, and these are undergoing regeneration. And then you will see that when you actually get the gases out over here, this is the steam plus CO2 that is going out. If you have the water that is, or condensate, or the steam that is going out, this is how will the condensate go out. So this gives you a showing an idea in reality, if you conceptualize it, how such bed will be operating, how many beds you will be needing, and those scheduling problem you solve separately, and then you design, find out the n number of beds and come up with a cycle design here. But this is the overall configuration that you consider. Now, when you have a vacuum here, so then you pull the vacuum here. So this goes to the vacuum, and then it goes to the CO2 compression train. And that is what the problem is. So that is something you cannot forget about that part. And I will say you why that thing actually keeps coming. Okay, any question here, anybody? Okay. Now, one thing which you have to remember is something called a cycle design. Maybe I was planning to do it sometimes also tomorrow as part of the tutorials, if I have time permits, that how to set up cycle in AdSim and discuss more about that and some mathematical nuances. But the conceptualization, I wanted to do it today. The first thing is that, as I said, you really should be solving a scheduling problem. The heuristics that I gave you, that one thing which you have to remember here is that if the CO2 that you are regenerating, only thing I said that when you do adsorption, it must be continuous, like all the beds should be in parallel. But what happens to the desorption? The gas that is coming out from the desorption, that is being compressed by the CO2 compressor. What happens that there is a gap between the desorption. So bed 1 dissolved now, and then there is a 5-minute gap After that, bed B comes for desorption. And then there is a 5-minute gap, then comes to the bed C. If there is a gap between the bed desorption time, the CO2 compression or CO2 compressor will not like it because it's going to zero flow, right? Or one bed is desorbing, so in the beginning of desorption, you dissolve lot of CO2, so flow rate is very high, and then towards the end of the desorption, the flow rate will go down. So you are talking about a fluctuating flow rate to the CO2 compression. So you have to be, that is why the scheduling problem is so important to solve here. This part is, my observation is that this part has been normally been very neglected in the literature, but I will point to some of the papers in this area, including one of our papers that where we actually tried to define it and do it like that. But the idea here is CO2 flow rate to CO2 compression with time. If it is like this is not acceptable. This is not acceptable at all. So this is one extreme. Other extreme is like this. This is also not practical because of this cycling process. So you will have to see something like this. So you basically say this is the acceptable variation. So this is the acceptable variability. Plus use a large surge vessel or storage vessel to smoothen it. So at the up front of it, you put a vessel which will actually take this and then it will smoothen this pressure, the overall systems in here. But this is something you have to keep in mind that going to zero is not acceptable. So that is why the challenge of the scheduling, that is why you need to solve an optimization problem to satisfy that constraint in there. Okay. Now, this bed design which we did for 90% capture from a subcritical pulverized coal plant for 644 megawatt. Notice that number of bed undergoing adsorption is 12. See the total number of beds, 43. So the other beds which undergoing other steps, in this case, there were actually 31 beds undergoing. That is for that basic TSA process that I discussed here. Like if you are doing this cycle. If you are doing this cycle, then there will be 3264. It just becomes exactly matched with the time. So you see the total number of beds is actually undergoing adsorption and desorption. This becomes actually very different. You see the cycle time also, how it becomes different. So as you are doing the bed design, all of these things are going to change, like optimal residence time, the adsorption cycle time, desorption cycle time. All of these are design criteria that you are keeping in mind for any of the system design. Okay. So when you try to develop the model, one questions come here is that are there differences? No, you use the same adsorber model for doing the regeneration. So mathematically, everything will work out the same way, but adsorption is taking place in presence of, say, CO2, nitrogen, moisture, and whatever. But desorption is taking place only in presence of maybe CO2 or steam. So you do not have nitrogen. So you are changing the composition of the gases completely. And that is where this becomes a tricky problem, that you have to change the boundary accordingly then. You may need additional model because of the embedded heat exchanger. This is not something directly AdSim model will give you that, but I'll show you, let's see how the tutorial goes tomorrow. We'll show you some of these advanced option, that how to include this heat exchanger and where to write the equations for any of those. As I said, that there could be change in the boundary condition. So as you notice here, so when the adsorption is taking place, the gas is coming in, but when you move to the desorption, instead of gas, it is a steam that is coming in. When it is going out, this is the flue gas going out, this is the steam plus CO2 going out. Then the idea is that when you have an adsorption, this is cooling water coming in, this is hot water coming in. So all of these actually leads to stiffness in the solver. And so that is why understanding Aspen custom modeler is so important, because many of these things, the bare bone Aspen AdSim model does not give you the directly in their library. You can build all of those, right? That is what all our papers are all in that area, because we tried to build all of those things. You can do it, but you have to be careful, because every time you are actually doing it, this is leading to a change in the boundary conditions. So that's the part you have to understand here. The other thing you have to keep in mind also is that the operating condition will change significantly. Like the environment which has got only nitrogen and CO2, it will suddenly see only steam and CO2. So the compositions will steeply change inside that adsorbent, and that's a problem because of, as we discussed for any Newton type of a solver, how to do that transition there. So there are tricks that you can do for doing that. Now, one question comes is, what type of cycle is optimal? The answer really depends on the feed composition and the available pressure at the boundary. If the feed contains large amount of contaminants like nitrogen in post-combustion flue gas, so this is different if you are considering a blast furnace gas versus you are considering a steel plant versus you are considering a pulverized coal plant or NGCC. What is actually in the boundary? Then first thing is that only let's say if you have large amount of nitrogen, just as you will expect in a power plant, only a moderate increase in the flue gas pressure is optimal. All our economic calculation shows if you go out from the blower regime to compressor regime, your economy will goes down, because you are compressing nitrogen, right? That is what the problem is. So that is why the pressure swing problem, only pressure swing has limitation for post-combustion capture. It's not expected to be optimal, because you cannot, if you look into the economics of it, compressing the large amount of gas consumes so much power. If you're trying to compress it, that actually causes economically unfavorable situation. So what you really want to do is that it is okay to compress some using a blower, but some temperature swing is expected to be needed. So it's basically a pressure temperature swing approach, where you can lower the pressure during desorption and temperature needs to be increased for desorption. So you can do a combination of both of them. I wanted to ask all of you a quick question. So when we do the pressure swing, so in the temperature swing, we do the desorption, right? So the thermal energy provide the energy for desorption. But in a pressure swing, I pressurize it and drop the pressure, I get depressurize it. Who provides the energy for desorption? Nothing is free, right? I talked about the no free lunch theorem, right? Nothing is free. So in temperature swing is obvious, I provide the energy and desorbs it. But in a pressure swing, I do not provide anything. I just basically drop the pressure and the gas is coming out. So where from the energy is coming from? in the compression state. So the power requirement for the compressor is the main parallel to temperature swing. So the thermal heat I provide versus the compressor power that I require, that is the thing that you need to compare to see where it is actually coming from, right? The other thing is that only moderate vacuum, if at all needed, is expected to be optimal, since CO2 need to be compressed to 150 bar. This is something you just need to look into the number to realize what I mean here. Assume CO2 is dissolved at, I put it like 150 bar, take that one itself, at 1 bar. Then compression ratio is 150 over 1 is equal to 150. If CO2 is dissolved under vacuum at say 0.5 bar absolute, then compression ratio is 300. And if I do it 0.25 bar, compression ratio becomes 150 by 0.25, 600. For many processes, this CO2 compressor actually consumes almost like 50% energy as the capture system itself, almost, when the CO2 is available at 1 bar. That is why only a very moderate vacuum is acceptable. And so even though all of those are mathematically possible, all of those works for other type of system, but for here, because we want to ultimately compress the product to such a high pressure, the vacuum is not expected to be economically optimal. For temperature swing, I would also like to mention that you desire the adsorption time is relatively high and the time for heating the bed for desorption is not very high. Because if you say I go from adsorption to desorption and if it takes me so long to heat up the bed, then the temperature swing will not work. That is why that embedded heat exchanger and the design of that embedded heating process is so critical from that perspective there. So that is why, as I said, embedded heat exchangers are very critical overall. So in the conclusions, I would like to mention that economics is it is not only the adsorption. Adsorption is only the part of the game. You must look into the desorption, and most cases it's actually the desorption that affects the overall economics. That has got the maximum impacts on the overall thing. So just looking at the adsorption can be very misleading. So total systems, you really need to look into it. And from that perspective, you need to come up with an appropriate design for this overall process. The cycle design is one thing which I'm missing here, and I have got a couple of minutes here, so I'll just show you quickly how it looks like, what it will look like here. But you must solve an optimization problem. This is a mixed integer linear programming problem, which we would not have time to cover as part of this class, but that's how those things are done. And I will basically first see if anybody has any questions. Otherwise, I'll show you how a cycle actually design looks like. Any questions? Okay, so I'll just show you graphically, but you show when you think about it mathematically, you have to pose this as an optimization problem. So I'll say the cycle design. I'll show you by a Gantt chart how it actually looks like. Assume 3 beds in parallel, say 30 minutes of adsorption time and say 5 minutes of non-adsorption time. So based on my calculation there, what was the thing, how it should be? I said 30. Remember that equation that I wrote for a heuristics. You can apply for simple calculation. 30 divided by 3, so 10, right? Should be greater than equal to, I said 5. So if I'm just using one bed, that should be sufficient. You see, if you have that equation written up, you can actually correspond to that one. So this is basically the non-desorption time, and this is my unknown. So I'll put a asking mark. And as a guess, I'll just put just one bed. If I do this, this is satisfied. So I basically saying total number of bed is total number will be 3 plus 1. So I need 4 bed for these systems, right? So let's see how it actually cycle that will look like. So if I'm actually doing it over here, so I will have so this basically means adsorption. This is my bed A, and this is, I'll put the scale below, and then assume that I'm starting it another one 10 minutes later. So this is 10, this is bed B. So this bed after this will go for desorption, and this bed will sustain for another 30 minutes, and then assume that I started another bed. This is 20, this bed C. And then what you really find there is that at that point of time, that 30 minutes later, I need a bed to start here. So this bed is after that. So adsorption, this thing, this is actually non-adsorption, and this is idling. Then this bed will go for 30 minutes. And here what happens is that this bed comes out, then it will go for the non-adsorption, then it will go for idling, and then it will start here. The same way it will happen with this bed, non-adsorption, and then idling, and then it will go for adsorption. And this bed will do the same thing, idling, and then it will go there. So what you will actually notice, so that is the point you need to follow along with me, look into here, right? After this, and then after that, it will go for regeneration and do the idling, and it keeps continuing with the adsorption here. So if you notice from here till here, this is your cycle time equal to this 30 plus 10, actually 40 minutes. After that, if you actually draw it in front of you, you will see that it will actually keep repeating. So I will have exactly the same thing. So if you look into this particular bed, here I started with here the regeneration. You see I'm again starting with the regeneration here. Here I spent already 20 minutes over here. I'll be starting about 20 minutes over here, and I'm starting here. Then for this bed, I have already started 10 minutes. I have got 20 minutes remaining. So these beds will keep going here like that, just like what we had over for these ones. So this is a repeating cycle that actually keeps going. And so the trick for this one is that you actually, when you start drawing it, you actually offset the time in the beginning, and then at one point of time it will actually catch up there. So that is how you do the Gantt chart. And if you have done a batch processing class, this is something which you routinely do. If you plot it in Excel, actually with these blocks, you should be able to find out that these overall systems become really repeating for these systems. So now the thing that is happening is that adsorption, non-adsorption, and you see there is a 5 minute of idling. You see there is a gap everywhere. So the CO2 compressor during this time is not getting anything. Then it is not getting anything. Then it is not getting anything. Then it is not getting anything here. So there is a gap of every 5 minutes. So what I can do here is, instead of idling, I just basically say, okay, instead of idling, let me do my all the desorption over 10 minutes so that it's not idling. I can do that for all of these things. So you see that the moment this bed is done, then the second bed is done. It goes to the second one, then it goes to the third one. It will be up to here, then goes to the third one, then it goes to the fourth one. So you see this, 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 this. It goes sequentially with the desorption. So the CO2 compressor will be happy about it. This one, actually, the best way to understand for you is to draw this in like even Excel, the way you draw the typically Gantt chart, like for your project scheduling and things like that. And when you start it, if you take this number, you just offset it by 10 minutes, 20 minutes, and you will see everything will actually align with this. So this is how you come up with really typical cycle design. But as I said, if you have got a really large number of bed, like you saw those crazy number that we had, right? Number of bed adsorption is 12 and 31. That one will require you to solve that problem actually, like you. Yeah, this guy, 12 and 43. That one actually tough to do it this way. I just wanted to show you the simple one, but you can read our paper there and see how all of these things are actually done. It's a little complicated, but for simple systems, you can do it. But this is important for your economic calculations. Okay, so I think it's about 12. I will stop here and see anybody has any questions for me. Yes. Oh, no, the offset, this is actually to align with the cycle. It does not matter actually. So what you really need to look into is here. This portion that I put in, from here onwards, you will see that it is repeating. So it does not matter. It's basically, because I do not know, so this is actually, I'm trying to catch it. When you actually do it in a optimization problem, it will directly jump onto this one. I'm actually just, it's kind of my initial guess. So that is what I'm landing onto it. But what you really need is a cycle from where it is repeating, which I showed here, right? You see now it is aligned, right? everything will be aligned, and after that it will be all other things will actually be exactly repeating. Where you started, that is where exactly you start. See, I'm starting with the regeneration here, and this is also starting with the regeneration. This is my cycle time, right? And if you see here, when I am here, I've spent 10 minutes into absorption, 20 minutes into adsorption. So after 10 minutes, it has to go for the desorption. So that is what it will be happening. This is the 10 minutes here. So this is the place it will go for that. Sorry, I was using this notation. Sorry. This guy will go through this, and then after that it will go through the desorption and all of that. So if you notice, the place to think about is this guy. So where you started and the next end where you end, these two should be exactly the same. Where you finish, you are starting it back here. This guy and this guy, it should be exactly be matching. This is the standard Gantt chart that which we draw for project scheduling, but this is how I actually prepped it there. So I just quickly wanted to show that. So it depends upon your jaw bend. These ones that which we consider that can withstand up to about 150 degrees centigrade. So we actually solve an optimization problem. So 150 degree means that I do not want to go for 150 degrees C. I may do it at 100. We come to almost close to the room temperature. Of course, it's not acceptable. Yes, it will actually. So that's why if you look into that MOF paper, we actually discussed that and looked into this one. Like if you're seeing it is coming to 65, I'm not showing the regeneration temperature here, but that is why you are exactly right. If you take it to 150, that temperature itself will not only take time, but also take a lot of energy. So that is why it's an optimization problem. You might actually like to dissolve at 110 or 15 or 105 to reduce your penalty and the time for doing that. But yeah, it's an optimization problem.
It is only CO2 is there, then okay, this temperature is okay. Suppose some SO2 also is there, then we cannot reduce the temperature to 105. Minimum temperature only it's maintained. SO2 formation also will take place. So
Yeah, that will.
the composition
It depends on the composition of the flue gas. Most cases, I think SO2 is something, most of them really do not like SO2. Most of the adsorbents, again, I'm not a materials guy, but my understanding is that most of the adsorbent do not like SO2. And then the problem is that the SO2 will, if it adsorbs, it will be mixed with the CO2 when you are sending it down. It can lead to corrosion of the pipeline. So most cases there is a scrubber that takes off the SO2. It generally KOH or NaOH scrubber, and that it scrubs the SO2 before, and then only it is actually fed.
Flue gas, even after all economic needs of heat recovery, is still above 100 degrees Celsius.
Right. So these ones, yeah, this one actually, a lot of these actually considers a direct scrubber before this. So even for the solvent-based capture, there is a direct scrubber first. So as you know, the direct scrubbers, when acceptable, they can give you the best temperature approach. So you spray water, that actually helps you both ways. It makes the gas saturated, especially for solvent-based, it's very common. And for these ones, actually, you can actually, right. So that means that it really depends on the adsorbent. For these ones, there is actually dehumidifier. So you first actually cool it down to the room temperature, then you separate out the water from the system before you feed it to this. Absolutely. Absolutely. The pre-processing steps are actually important. That's why when you look into this to see the entire plant, actually, we have actually a lot of simulations that shows the entire plant. It just looking into the capture plant gives you the part of the story. Now you have to look into plant-wide system. Okay, other questions here? If not, yes.
That will be capillary actions and all. So it will bring down the temperature within the bed and then split this out.
This is something only a mathematical model will tell you, and hoping that you are way above. So it depends upon what is the design cushion that you want to take or margin of design that you want to take. But you are absolutely right, because what happens is that the steam that you are injecting, the partial pressure of steam actually keeps changing through the system, and of course the temperature keeps changing. So you have to basically, if you see all our code there is a relative humidity calculations everywhere through the entire system to ensure that your relative humidity is below certain percentage, like 70-80% or whatever design cushion you want to take. But you must take those calculations there, absolutely. So the trick is, with the moisture, always do a relative humidity calculations and ensure that that does not exceed certain value to avoid the condensation. Yeah. Anything else? Okay, very good. So we'll now break. Um,
There is one question from online participant,
Okay.
Rajiv. So he's asking that how much energy, DOE, Department of Energy, we need to dissolve in gigajoule per ton of CO2.
How much energy is needed?
To dissolve the CO2 according to DOE in gigajoule per ton.
Because of?
In gigajoule per ton.
Okay. Okay, so how much energy we need? So I think that's a good question, which I was probably planning to cover something yesterday as part of the performance, but let's discuss this mathematically here. Right. So if you look into any of these steps here, so how much energy do we need? First is the heat of desorption. So this will depend. So if you have a physical, if you have physisorption, generally 15 to 50 kilojoule per mole. If you have a chemisorption, this is generally 65 to 120, 130 kilojoule per mole. Kilojoule per mole. So it depends on that one. This is the minimum heat that you must provide, plus the heat sensible heat needed to heat up the bed from end of adsorption temperature to the desorption temperature plus heat losses with the outgoing gas, which is CO2 plus H2O plus any other loss to the environment. So this is all comes from your simulation. So what you have to really think about it is that this gas that is going out, like when you use the hot water, like this is outgoing gas here, and the dissolved CO2 and nitrogen that goes out, that gas is actually taking away the heat from your system. So if it is going out at say 120 degree or 110 versus 150 degree, that is actually a heat that you are losing from the bed. You can do a heat recovery, that's a different case. But if you don't consider the heat recovery, that gas is also taking out that heat. And then the bed temperature needs to be heated up. That is the sensible heat, because I end adsorption say at 65 degree and I start the desorption at 110 degree. I need to heat up for that entire delta. And if I go to 150 degree, the delta may be very high actually. So that thing, and then any other losses to the environment, like from the wall of the vessel or anything, that needs to be taken into consideration. Okay, does that answer your question? Like if you check, if